Welcome back. In the previous session, we have discussed the time domain representation of quadrature phase shift keying digital modulation scheme with respect to mathematical expression as well as the graphical representation. Moreover, we have identified the message points in the signal constellation, and also we have discussed to determine the decision boundary for detecting each of the message points at the receiver side. With the information studied with the help of the previous session, we are now going to see the generation and detection of coherent quadrature phase shift keying signal. So let us start with the QPSK transmitter. And the binary message sequence is given as the input to the QPSK transmitter. So let us consider the binary sequence as like this: 1011010010. And we know that all these are odd positions, odd numbers, odd number indices. Similarly, these are all the position mentioning even number indices. And in QPSK, we are going to consider the die bit. This is one die bit, this is one die bit, this is another die bit. Similarly, here we are having 5 die bits as we are having 10 bits. In BPSK system, this 1011010010 is represented by a pulse waveform 1 0 1 1 0 1 0 0 1 0. This is the waveform in the case of BPSK, and this is the symbol period, or otherwise this is called as the bit duration, where we can say that TS as symbol duration and TB as bit duration. Now, in the case of QPSK, we are going to consider these 2 bits. Hence, in QPSK system, the symbol 10 is represented by TS, which is representing twice the bit duration as in the case of TB. But generally, this TS should be same, so that we are considering this TS within this duration, within the duration of BPSK, by reducing the time duration by half of the bit duration of the BPSK input binary sequence. Hence, we can, for the duration of 5 bits, we can accommodate 10 number of bits. So in the case of QPSK, what we are going to do is, we are going to split these informations into 2 sequences. One is odd number sequences and another one is even number sequences. By the way, in QPSK, we are going to represent it in parallel manner, that is odd number sequence on one hand and even number of sequence on another hand. Odd number sequences are 1, 1, 0, 0, 1. So 1, 1, 0, 0, 1. So 1, 1, 0, 0, 1. And similarly, the even numbered sequences can be represented as 0, 1, 1, 0, 0. So it is represented like this. And here, this is represented as TB or TS. And this is, that is, within this one symbol period, it is possible to transmit 2 bits simultaneously. Hence, in the case of BPSK, we need 10 times of symbol period to transmit these 10 bits of information, whereas in the case of QPSK, it only requires 5 times of the symbol period to transmit these 10 bits. Hence, it is faster than the BPSK, twice than BPSK. That is why the data rate of the QPSK is considered as the twice of the BPSK system. Okay, now let us consider the binary sequence 10110100, and this is sent to a polar non-return to 0 line coder. So the polar non-return to 0 line coder will produce the corresponding polar representation, electrical waveform for these binary sequences. Generally, in polar non-return to 0 line encoding, binary data 1 is represented by positive voltage and binary data 0 is represented by negative voltage. Hence, this 1 is represented by plus square root of ES by 2. Similarly, This 0 is represented by minus square root of ES by 2. The third one is represented by plus square root of ES by 2. The fourth one is represented by plus square root of ES by 2. And fifth 0 is represented by minus square root of ES by 2, and it will go on. Sorry. This is for 10110001. Now, the binary sequence 1011001 has been represented by the electrical polar waveforms which is having binary magnitude levels plus square root of ES by 2 and minus square root of ES over 2. And now the demultiplexer is used to convert this serial data into parallel form, and it has two channels. One is in-phase channel and another one is quadrature channel. The terms come from the fact that each of the channel is having a product modulator supplied by a sinusoidal signal, and the in-phase channel is having a sinusoidal signal which is in phase with the carrier signal, because carrier signal C of t is considered as cos 2 pi fct. As it is having the similar phase with in phase with the carrier signal, it is called as in-phase channel. And the another parallel channel which is also having a product modulator that is supplied by a sinusoidal signal which is having a 90-degree phase shift of the carrier signal. That is why it is called as quadrature channel. And the intention of the demultiplexer is to split the binary sequences or die bits into even numbered binary data and odd numbered binary data, and allowing it to the in-phase and quadrature channel. And all the odd number binary data are allowed to the in-phase channel, whereas the even numbered binary data are allowed to the quadrature channel. Hence, for the binary data 1, 0, the output of the polar non-return to 0 line encoding is plus square root of ES by 2 and minus square root of ES over 2. So, odd number pulse is going to the in-phase channel and even number pulse is going to the quadrature channel. Hence, it is multiplied with this function and provides at the output of the in-phase channel as plus square root of ES by 2 multiplied by 2 by TS cos 2 pi FCT. And this is in the quadrature channel, the output of the quadrature channel is minus square root of ES by 2 multiplied by, TB or TS, any functions we can use, sine 2 pi FCT. Now the QPSK signal is the sum of these two signals. So it will be written as plus square root of ES by 2, square root of 2 by TB cos 2 pi FCT minus square root of ES by 2, square root of 2 by TB sine 2 pi FCT, which is nothing but S4 of t. Similarly, for the next binary sequence, 1, 1, the next two symbols will be selected and the odd number symbol will be allowed here. Similarly, the even number symbol is allowed here. So both are having the positive terms. So the output will be written like this, and that will be represented by S1 of t. So this is representing the first two bits are producing S4 of t, and the next two bits are producing the symbol S1 of t, and the next two symbols are producing S3 of t, and the next two symbols are producing S2 of t. That means we know that the signal constellation map, that is square root of ES by 2, square root of ES by 2 is representing the message point 1 for the corresponding binary data 1, 1. Similarly, minus ES by 2 plus square root of ES by 2 will representing the message point S2 for the corresponding binary data 0, 1, and minus square root of ES by 2 minus square root of ES by 2 for the corresponding message data 3 for the binary input die bit 0, 0, and plus square root of ES by 2 and minus square root of ES by 2 for the message bit 1, 0, and the corresponding message point is S4. By this way, the QPSK signal is being generated with the help of this transmitter. Let us discuss the coherent deduction of QPSK. So the transmitter is assumed to transmit any one of these four symbols, S1 of 2, T, S2 of T, S3 of T, and S4 of T, depending on the corresponding die bit binary inputs. And this S of T is allowed through the channel, and we are going to consider it in two ways. One is noise-free channel, and another one is AWGN channel. In noise-free channel, R of T can be written as Si of T alone, And for additive white Gaussian channel, R of t, the received signal R of t at the input of the receiver is assumed to be R of t is equal to Si of t plus N of t for I is equal to 1, 2, 3 and 4. And here N of t is additive white Gaussian noise with zero mean and variance N0 by 2, where N0 is the power spectral density per unit bandwidth. So let us first consider the noise-free environment. In this noise-free environment, we are going to operate this coherent QPSK receiver. And this coherent QPSK receiver is having two channels, in-phase channel and quadrature channels, which are working parallelly to consider the die bits symbols in each of the channels. Similarly, the odd sequence of binary die bit is determined by the in-phase channel. Similarly, the even numbered binary data is identified by the quadrature channel with respect to the transmitter. And these two parallel channels are having two binary receivers. In-phase channel is having one set of binary receiver and quadrature channel is having another set of binary receiver, which is of coherent type. Here the term coherent comes from the fact that the carrier frequency supplied to the product modulator is synchronized in frequency and phase with respect to the carrier signal generated by the local oscillator at the transmitter. And it consists of a correlator which is composed of a product modulator followed by an integrator, and the output of the correlator is given to a decision device and it is compared with a threshold value, and the decision device is taking decision in favor of 1 if R1 is greater than lambda, or it will decide in favor of 0 if R1 is less than lambda. Similarly, the same process occurs in the quadrature channel also, except only one thing. In the in-phase channel, the signal which is in phase with the carrier signal is given as an input to the product modulator, whereas in quadrature channel, the sinusoidal signal which is having 90-degree phase shift of the carrier signal is given to the product modulator. So let us discuss how this receiver is receiving the binary data. So let us assuming a noise-free environment. So R of t, let us assume R of t is equal to S1 of t. That is, we are assuming that S1 of t is transmitted by the transmitter. So if S1 of R of t is equal to S1 of t, then the output of the product modulator is nothing but S1 of t multiplied by phi1 of t, and the output of the product modulator in the quadrature channel will be S1 of t and phi2 of t. And the output of the in-phase channel is the integration of 0 to 2EB S1 of t phi1 of t dt, which is equal to integral of 0 to tb. S1 of t can be written as plus square root of Es by 2 phi1 of t dt. And integral of phi1 of t will become 0 to tb phi1 of t the whole square dt, which is nothing but unity. Hence, the energy of the orthonormal basis function is 1. So, the value of R1 is equal to plus square root of Es by 2. Similarly, for R2, S1 of t is given the output of the product modulator is S1 of t phi1 of t, and the output R1 can be written as integral of 0 to Ts S1 of t phi1 of t dt, which can be written as S1 of t can be written as S11 phi1 of t plus S12 phi1 of t dt phi2 of t dt. Multiplied by phi1 of t dt. Hence, it is getting integral of 0 to Ts S11 phi1 of t the whole square dt plus S12 integral of 0 to Ts phi1 of t phi2 of t dt. As orthonormal basis function is having unit energy, this term will become 1, and the orthonormal basis functions are orthogonal to each other. So phi1 of t and phi2 of t are orthogonal to each other. So this term will become 0. So hence R1 become S11 into 1 plus S12 into 0. Hence R1 is equal to S11. Similarly, R2 will be determined by integral of S1 of t phi2 of t dt. Hence, if you substitute like this, you will get integral of S11 phi1 of t phi2 of t dt plus integral of S1 to integral of phi 2 of t the whole square dt. So this will become 1, this will become 0. So R2 will become S12. Hence R1 is S11 and R2 is equal to S12, and we know that S11 is equal to plus square root of ES by 2 and S12 is plus square root of ES by 2. So the division device is comparing the R1 with the lambda is equal to 0, because the threshold has to be chosen as 0, for which I have already explained in the previous session. Hence, as R1 is greater than lambda, the decision device is taking decision in favor of 1. Here also in the quadrature channel, R2 is also greater than lambda. Hence, the quadrature channel is also deciding in favor of the binary data 1. And these ones present in the in-phase channel and quadrature channel are multiplexed, and it is transmitted as a die bit, and it is sent to the estimated as 1-1 binary sequence, determining the binary sequence as 1-1, which is equal to the transmitted binary die bit. This is the similar case for all other binary transmission, like S2 of t, S3 of t, and S4 of t. Now, let us discuss all these receptions with the help of this coherent QPSK receiver in the presence of additive white Gaussian noise. Hence, R of t will become S1 of t plus N of t. That is, S1 of t is the transmitted symbol and N of t is the additive white Gaussian noise. So R1, this will become S1 of t, phi 1 of t plus N of t into phi 1 of t, and this will become S11 plus N1. Similarly, R2 will become S12 plus N1. And now, S11 and S12, we know that S11 is equal to plus square root of ES by 2, and S12 is equal to plus square root of ES by 2, so that this will be written as plus square root of ES by 2 plus N2. Hence, we can say that generally, this is the coordinates where S11 and S12 are meeting. This is the original message point located in the signal constellation. And now the noise is in such a way that the N1 will make this to move this side. This is the addition of N1, and N2 will make an addition like this in these positions. By this way, this can move on any of these quadrants, so that it is assumed that it is compared with the decision device, whether if both phi 1 and phi 2 are having the positive values, then we can choose it in favor of the binary die bit data 1-1. If the noise energy is very much greater than the symbol energy, then there is a possibility for entering into this portion, that is from the first quadrant to the fourth quadrant, or from the first quadrant to the second quadrant, depending upon the values of N1 and N2, which will create a wrong deduction of 0, 1 or 1 0, which consists of 1 bit error, which will lead to probability of error, and that will be discussed in the next session. And these are all the theoretical parts which I have already explained with the help of block diagram.